We will now analyze the case of a reinforced concrete cross-section subjected to bending with axial force. Well, the computation of the stresses over a cross-section on which we have bending and axial force can be done with two different approaches according to the different situations we may have due to the effects of the applied loads. Well, basically, we can have a high load eccentricity or a small load eccentricity. Well, in this situation, the neutral axis falls within the cross-section and divides the cross-section into portions, one which is in compression and one which is in tension. The section we consider in this case is therefore a partialized cross-section. Or we may be in a situation with a small load eccentricity. In this situation, the neutral axis is external with respect to the cross-section, so in case of compressive load, we will have a fully resistant cross-section. In case of only tensile forces, we have that in our cross-section, the steel is the only material, the only component which resists. So basically, this is the situation over our cross-section when we have an eccentric axial load. We have a rectangular cross-section, this is the centroid of the cross-section, and we have an external compressive load N applied with an eccentricity E. So basically, the action of this eccentric axial force is equal to the action of a centered axial force N plus a bending moment M, which is equal to N by E. So we can also define the eccentricity E as the ratio between M and N. And this is one situation in which on our cross-section we have a bending moment and an axial force acting together. So in order to determine in which between the first two situations presented at the beginning we are, so if we are in case of high load eccentricity or small load eccentricity, we have to evaluate the position of the point of application of the load with respect to the central core of inertia of the cross-section. While the central core of inertia is the area within which the eccentric axial force falls in such a way that the neutral axis does not intersect the cross-section of the beam. Let's consider the case for a rectangular cross-section. Well, we have G, which is the centroid of the resistant cross-section. YGS is the distance of the centroid from the superior fiber of the cross-section, and YGI is its distance from the inferior fiber of the cross-section. The one highlighted in gray is the central core of inertia for a rectangular cross-section, and we have indicated with ρ ns and ρ ni the dimensions of the central core of inertia along the y-axis, let's say, of our cross-section. They are defined in this way. So, ρ ns is equal to ρ squared over ygi, and ρ ni is equal to ρ squared over ygs, where ρ is the radius of inertia of the cross-section, and it is equal to the square root of j over a, where j is the moment of inertia of the homogenized cross-section with respect to the centroid axis, and a is the homogenized cross-section area. Well, ai is the homogenized cross-section area. Well, for the rectangular cross-section, if we consider only the concrete for sake of simplicity, we have that G is centered, so YGI and YGS are equal to half of the height of the cross-section. We have, so for our rectangular cross-section, ρ, which is equal to the square root of j over ai. So it is b h cubed over 12, that is the moment of inertia with respect to the centroid, to the power of 1/2, since we are inside the square root. The area of the cross-section is, of course, b by h. So ρ is equal to h over the square root of 12. We can calculate ρ ns, that is ρ squared over ygi. So we have h squared over 12 over ygi, which is half of the height of the cross-section, since the centroid G is centered. The result is equal to h over 6, which is also equal to ρ ni. So in this case, in which we are considering only the concrete, the cross-section is symmetric, and so also the central core of inertia is symmetric. The dimensions ρ ns and ρ ni are indeed equal. So basically, in order to establish if we are in the situation of high load eccentricity or in the situation of small load eccentricity, we have to compare the load eccentricity with the dimensions ρ ns and ρ ni of the central core of inertia for the cross-section we are considering. We will now analyze more in detail the case of a small load eccentricity. We have a reinforced concrete rectangular cross-section. We have an eccentric external axial load applied, N, and the point of application of N is point C. The eccentricity is E. And we have seen that the action of this force, of this eccentric axial force N, is equivalent to the action of a centered axial force N plus a bending moment M, which is equal to N by E. So we have that the eccentricity E equal to M over N, in case of small load eccentricity, is bounded in between the two dimensions of the central core of inertia. So in case of small load eccentricity, we have ρ ns lower than E, lower or equal than ρ ni. So the point of application of the axial force falls within the central core of inertia. So in this case, the neutral axis is external, or at limit coincident with an extreme fiber of the cross-section. In this situation, the axial force is a compressive axial force, so the cross-section is fully resistant. So in this case, we can use the effect superposition principle in order to analyze and evaluate the stresses on our cross-section. We will consider now, for sake of simplicity, a symmetric rectangular cross-section having symmetric reinforcements. Well, in this situation, the centroid of the ideally resistant cross-section is coincident with the centroid of the concrete cross-section. We have an eccentric axial force with an eccentricity E. The neutral axis falls out of the cross-section at a distance, and we have indicated with X the distance between the point of application of the axial force N and the neutral axis. H and B are the cross-section dimensions. C is the concrete cover, AS is the steel in tension, AS prime is the steel in compression. We are considering symmetric reinforcements. So the effect of the axial force N is equivalent to the effect of a centered axial force N plus a bending moment M, as we have already observed. So by using the effect superposition principle, we can compute the stresses on our cross-section, summing up the stresses given by the presence of a centered axial load and the stresses given by the presence of the bending moment. So we will consider these two stress diagrams. So the first one on the left is the stress diagram given by the presence of a centered axial force. And the stresses on concrete is indicated as sigma Cn. While the diagram on the right instead is the diagram if we consider only the presence of the bending moment M. We have indicated with sigma Cm the stress in concrete in this situation, and with R the neutral axis if we have only flexure on our cross-section. In particular, we have that sigma Cn, because of the presence of the axial load, is equal to N over Ai, as in the case of a cross-section subjected to uniform compression. And sigma Cm, is equal to M over Jri by H over 2, which is the stress in concrete in case of flexure, and we are considering Jri, which is the moment of inertia of the resistant cross-section with respect to the neutral axis R, considering only the flexure. And in this case, R has a distance from the superior fiber of the cross-section equal to H over 2. And this is the way in which we can compute sigma Cm. So the stress on the cross-section are then computed considering the effect of the compressive axial load plus the effects of bending in the following way. So we have that sigma C on the superior fiber of the cross-section is sigma Cn plus sigma Cm, so we have N over Ai plus M by E, which is the bending, over Jri by H over 2. Sigma C on the inferior fiber of the cross-section is equal to sigma Cn minus sigma Cm, so it is N over Ai minus M by E over Jri by H over 2. Then we have sigma S prime, which is N, the homogenization coefficient, N over Ai plus N by the bending over Jri by H half minus C, which is its distance from the R axis. And finally, sigma S, which is N over Ai minus N by the bending moment over Jri by H half minus C. we can draw here the final stress diagram, which is the red one. Well, remember that in order to draw all the stresses in the same diagram, we have to consider for the steel the values sigma s prime over m and sigma s over n. And of course, the stresses goes to 0 on the neutral axis. So this is the diagram that is the sum of the diagram sigma n and the diagram sigma m. Well, I have not specified that in the previous formula AI was equal to BH plus N, the homogenization coefficient by AS prime, plus NAS. The moment of inertia JRI was equal to BH cube over 12 plus NAS prime that multiplies H half minus C squared plus NAS that multiplies H half minus C squared. And rho ID, the radius of inertia of the cross section, is equal to JRI over AI. So by knowing the radius of inertia, we can compute the values of the dimensions of the central core of inertia and establish if our eccentricity is bounded in between them. So determine if we are in case of small load eccentricity. Well, let's make now some observations. The first one, if we have unsymmetric reinforcements, the centroid of the resistant cross-section does not coincide with the centroid of the concrete cross-section. Well, in this case, represented in the figure, we have AS greater than AS prime. Well, we indicate as G the centroid of the concrete cross-section and GID the centroid of the homogenized cross-section. So we have, in this case, rho NS is different from rho NI. And indeed, the central core of inertia is not symmetric. And the dimensions of the central core of inertia are different since the distances of the centroid of the homogenized cross-section with respect to the extreme superior fiber and the inferior fiber are different. If you remember the formula with which we have determined the dimensions of the central core of inertia. Well, the second observation is that in case of bending plus tensile axial force, the resistant cross-section area is only the steel area. So we have to have both AS and AS prime in order to have the equilibrium. We cannot have only the tensile reinforcements since the concrete is not working in tension. We will now analyze more in detail the case of high load eccentricity. In this case, as already observed, we have the point of application of the load which falls out of the central core of our inertia. So we have that the load eccentricity E is greater than the dimensions of the central core of inertia rho n. So in this case, we have the neutral axis, which falls within the cross-section, and we will consider partially resistant cross-section. So in this situation, we can no more use the effect superposition principle. And we have to consider, on our cross-section, the translational and the rotational equilibrium in order to find the neutral axis position and the stresses in the concrete and in the steel reinforcements. We consider now this rectangular cross-section. We have the point of application of n, which is external with respect to the cross-section, and the point of application of n is point C, with an eccentricity E between G, the centroid of the resistant cross-section, and the point C. And we have also indicated with X the distance from the neutral axis and the extreme superior fiber of the cross-section. We can see that the neutral axis falls within the cross-section. And we have also indicated with E prime the distance between N and the most compressed fiber of the cross-section. C is the concrete cover, and D is the distance between the tensile reinforcement and the most compressed fiber of the cross-section, as usual. We consider this stress diagram, in which we have sigma C, the stresses of the concrete in compression. We highlight the values of the stresses in correspondence of the steel reinforcements. So we have sigma S prime over N for the compressed reinforcement and sigma S over N for the tensile reinforcement. Below the neutral axis, the stresses in concrete is represented by a dashed line, since we are considering the concrete not resisting to tensile forces. So we consider an infinitesimal strip on our cross-section, let's say here. The Y. So we can write the translational and the rotational equilibrium equations. So for the translational equilibrium, we have to consider the resultant of the compressive stresses on the concrete, which is the integral between 0 and x. X is the position of the neutral axis of the generic stress sigma c on the y fiber by the b, the width of the cross section in the y, plus the resultant of the stress on the steel in compression, so AS prime by sigma S prime, minus AS sigma S equal to N, the external applied axial force. We can also consider the rotational equilibrium with respect to the neutral axis. That is the integral of sigma c of y b y dy, where y is the distance of the generic y fiber from the neutral axis, plus a s prime sigma s prime by the distance of the compressed reinforcement from the neutral axis, which is x minus c, plus as sigma s by d minus x equal to the external force N multiplied by its distance from the neutral axis, which is dN, where dN is x plus E prime in our figure, which is this one. Well, because of the linearity of the stress diagram, we may evaluate the stresses in concrete and in the steel with the following formulas. I'll write them here. So we have that sigma c of y is equal to sigma c, which is the stress in the most compressed fiber of the cross section, over x by y. And this is the stress in concrete on a generic y fiber. Then sigma s, the stresses in the tensile reinforcement, is equal to N by sigma c over x by d minus x. And sigma s prime is equal to N by sigma c over x by its distance from the neutral axis, which is x minus c. Well, they are simply calculated with linear proportions considering the linearity of the stress diagram. By substituting these relationships for the stresses in the equilibrium equations, we obtain these two expressions. The first one is the translational equilibrium equation. We obtain this relationship Well, in this expression, I've just substituted the values for the stresses in the concrete and in the steel that we have previously determined, and I have taken out from each contribution the term sigma c over x. Then, well, by solving the integral, we obtain bx squared over 2. That is sigma c over x by Sni equal to n. And in this expression, Sni, which is the term in the parentheses, is the static moment of the homogenized resistant cross-section. Well, from the second equilibrium equation, so from the rotational equilibrium equation, by substituting the values of the stresses, we obtain, well, we take out the term sigma c over x that multiplies these quantities, equal to n by dn. We solve the integral, so the expression becomes this one. It is bx cubed over 3 plus the contributions of the steel reinforcements Well, the term in the big parentheses is the moment of inertia of the homogenized resistant cross-section. We recognize it since we have already defined it for a rectangular cross-section subjected to flexure. So we have sigma c over x that multiplies jni equal to n dn. So jni is the moment of inertia of the homogenized resistant cross-section with respect to the neutral axis. So the unknowns of these two equations are sigma c and eggs. By considering the two relationships just found, we can write, so basically the unknowns are sigma c and eggs. So by considering the relationships previously found, we can write that sigma c is equal to n over the static moment Sni by eggs, and sigma c from the rotational equilibrium equation is n by the n over the moment of inertia Jni by eggs. So by equating these two expressions, we obtain Jni over Sni equal to dn, which is eggs plus E prime. And E prime, if you remember our initial scheme, is equal to E minus h over 2, which is also equal to m over n minus h over 2, where m is the bending moment produced by the eccentric axial load, and it is equal to n by E. Well, if we now substitute in this expression the expression for the moment of inertia Jn and the static moment Sn, we obtain a third-order equation from which we are able to calculate the neutral axis position. The third-order equation is this one. Well, sorry, in the second term we have 3e prime eggs squared. Well, I have not reported all the passages, but this third-order equation is determined by substituting the expressions for Jn and Sn in this equation here. And by making some simplifications, of course. This equation has a unique real solution, so by solving it we are able to find x, the neutral axis position. Once we know the neutral axis position, we can evaluate the stresses using this relationship. So we find the neutral axis position, and then we can calculate the stresses on the cross-section. So sigma C is equal to n over Sni by x. Sigma S prime is equal to n, the homogenization coefficient, by n Sni by x minus c. And finally, sigma S is equal to n, the homogenization coefficient, by n over the static moment Sni, multiplying d minus x. And we have also found the stresses on concrete and on the steel reinforcements in case of high load eccentricity. We will now consider an exercise on the determination of the stresses in a reinforced concrete cross-section subjected to bending with axial force with small load eccentricity. Well, the characteristics of the cross-section are the following. So we have a base B equal to 300 millimeters. The height of the cross-section is 600 millimeters. The concrete cover is 30 millimeters. So D, which is equal to H minus C, is equal to 570 millimeters. AS, the tensile reinforcement, is composed by 6 phi 16. So the total area AS is equal to 1,206 square millimeters. AS prime (3 phi 16), well, sorry, 4 phi 16 is equal to 804 square millimeter. The external axial force applied, N, is equal to 500 kilonewton. And the eccentricity, E, is equal to 80 millimeters. Here is the cross-section we are studying. So in order to establish if we are in a situation of a high load eccentricity or a small load eccentricity, we have to calculate the dimensions of the central core of inertia. And we will do it both by considering the presence of the reinforcements or by neglecting the presence of the reinforcement and considering only the concrete. We will first consider the presence of the reinforcements. Well, we have to calculate the homogenized cross-section area, AI, which is, as you know, B by H plus N AS prime plus N AS, which gives 300 by 600, which are the dimensions of the cross-section, plus 15, which is the value of the homogenization coefficient we use, that multiplies the sum of the reinforcement area. So 804, which is AS prime, plus 1206, which is AS. So AI is equal to 210,150 square millimeters. We now calculate the position of the centroid of the homogenized cross-section with respect to the superior fiber of the cross-section. So we calculate YGS, that is equal to SS over AI. And SS is the static moment of the cross-section with respect to the superior fiber. So we can write B H squared over 2 plus NAS by D, which is the distance of the tensile reinforcement from the superior fiber, plus NAS prime C, that is the concrete cover, over the homogenized cross-section area, which is BH plus NAS prime plus NAS, as before. That results equal to, I report here the numbers. So we have 300 by 600 squared over 2 plus 15 by 1206 by 570 plus 15 by 804 by 30 over the value of the homogenized cross-section area we have already determined, that is 210,150. Well, the final results for YGS is equal to 308 millimeters. We now calculate the moment of inertia of the homogenized cross-section with respect to the centroid. So we have JI, that is equal to the moment of inertia of the concrete, that is the sum of these two components, of course, plus the contribution of the compressed reinforcement, NAS prime YGS minus C squared, plus the contribution of the tensile reinforcement, NAS by D minus YGS squared, which, substituting the numbers, is equal to 300 by 600 cubed over 12 plus 300 by 600, that multiplies the distance between the centroid of the homogenized cross-section and the centroid of the concrete cross-section, squared, plus 15, the homogenization coefficient, by 804, that multiplies the distance between the compressed reinforcement and the centroid of the homogenized cross-section, which is 308 minus 30 squared, plus 15 by the tensile reinforcement area, which is 1,206. That multiplies the distance from the tensile reinforcement to the centroid of the homogenized cross-section, also in this case. So 570 minus 308 squared. So finally, we will obtain Ji equal to 7,585 by 10 to the power of 6 millimeters to the power of 4. So we are now able to calculate the radius of inertia of the cross-section, that is rho I. We calculate rho I squared, that is the ratio between Ji and Ai already determined. That is equal to 36,095 square millimeters. So by knowing the radius of inertia now, we can calculate the dimensions of the central core of inertia, which are rho n I and rho ns. Well, rho ni is equal to rho I squared over ygs, the position of the centroid of the homogenized cross-section with respect to the superior fiber of the cross-section. We obtain this ratio with the values we have already calculated. So rho ni is equal to 117 millimeters. Rho ns is equal to rho I squared over ygi, that is the distance of the centroid of the homogenized cross-section with respect to the inferior fiber of the cross-section. So we can also write rho I squared over h minus ygs. That is, substituting the numbers, this relationship here, equal to 124 millimeters. Well, we calculate the value of the eccentricity of the axial force with respect to the centroid of the homogenized cross-section, which is equal to E, that is 308, which is the distance from the centroid and the superior fiber of the cross-section, minus half of the height of the cross-section, plus 80, which is the eccentricity of the axial force with respect to the centroid of the concrete cross-section. That gives 88 millimeters. So since we have, in this case, rho ns equal to 124 millimeters greater than E, which is 88 millimeters, we can say that we are in case of a small load eccentricity. Well, just for comparison, we will now calculate the central core of inertia, neglecting the presence of the reinforcements. So we have the area of the concrete only, in this case A, which is B by H, of course. Which gives 108,000 square millimeters. Then we calculate the moment of inertia of the concrete, which is simply BH cubed over 12. That is equal to 5,400 by 10 to the power of 6 millimeters to the power of 4. We calculate the radius of inertia, rho, that is J over A. And it is also equal, if you remember, to H squared over 12 for a rectangular cross-section considering only the concrete, which is 3 by 10 to the power of 4 square millimeters. Well, in this case, we have YGI equal to YGS, the distances of the centroid from the superior and inferior fiber of the cross-section. They are, of course, both equal to H over 2, which is 300 millimeters. And we can now calculate rho NS and rho NI, which are equal to rho squared over YGI or YGS. It's the same since they are equal. That is H squared over 12 by 2 over H. That is H over 6 equal to 600 over 6 equal to 100 millimeters. We have already seen in the previous lectures that the dimensions of the central core of inertia for a rectangular cross-section, considering only the concrete, is equal to H over 6. So in this case, the value of the eccentricity E with respect to the centroid of the concrete cross-section is equal to 80 millimeters. So we have that rho NS equal to 100 millimeters is greater than E, which is 80 millimeters. So we are in a situation of small load eccentricity, as we have already observed before. Well, and the differences between the values of rho and S calculated by considering the presence of the reinforcements or by neglecting it is 24 millimeters. So we have already said that we are in case of small load eccentricity. Which means that the cross-section is full compressed. So for the calculation of the stresses on concrete and on the reinforcements, we can use the formulas already seen in the previous lecture, which are the following. Well, we have sigma C max, which is on the superior fiber of the cross-section, which is equal to N over A plus N by E, that is the moment produced by the eccentric axial force, over J, by H over 2, which is the distance from the centroid to the most compressed fiber of the cross-section. Well, since the differences from the two cases of the calculation of the central core of inertia by considering the presence of the reinforcements or by neglecting it are small, we are now considering the presence of only the concrete. So we are considering A as the area of the concrete cross-section and J as the moment of inertia of the concrete cross-section. So I'll write the formula with the numbers. Well, N is 5,000 kilonewton. We want the stresses in megapascals, so we will consider in the formulas Newton and millimeters. Well, the result is 2.8. That is the stress given by the centered axial load, plus 2.2, which is the stress given by the presence of the bending moment. That is 5 megapascal. Then we have sigma C min, which is the value of the stress in concrete in the inferior fiber of the cross-section. That is N over A minus N by E over J by H half. In numbers, we have this relationship. The result is equal to 2.8 minus 2.2, so we get 0.6 megapascal. We can also calculate the stress in the compressed reinforcement, sigma S prime, which is the homogenization coefficient by N over A, plus the homogenization coefficient by N by E over J, that multiplies the distance between the compressed reinforcement and the centroid. That is equal to this expression. Equal to 71.7 megapascal. Well, in the same way, sigma S is equal to n by n over A minus n that multiplies n by E over J by H half minus C, also in this case. That gives, without substituting all the numbers, 11.7 megapascal. And this is the way in which we can determine the stresses on our cross-section in case of small load eccentricity. But let's now make another exercise on a reinforced concrete cross-section subjected to bending with axial force. The geometric characteristics of the cross-section, which is rectangular, are the following. So the base is 300 millimeters. The height is 600 millimeters. The concrete cover for both the reinforcements is equal to 30 millimeters. Therefore, D is equal to 570 millimeters. AS and AS prime are equal and made out of 6 bars Phi16 for a total area of 1,206 square millimeters. And the axial force, the eccentric axial force that acts on the cross-section is 300 kilonewton, applied at a distance E prime from the superior portion of the cross-section equal to 200 millimeters. This is the concrete cross-section we are considering. The axial force N is applied externally at a distance E prime equal to 200 millimeters from the superior fiber of the cross-section. Well, so in this case, for sure, the point of application of the eccentric axial force falls out of the central core of inertia. So we are in the case of a high load eccentricity, and we will have a partialized cross-section. So we will have the neutral axis that we can assume, for example, in this position. So the upper portion of the cross-section, depicted in gray, is compressed. And we indicate with X the position of the neutral axis with respect to the superior fiber of the cross-section. So according to what we have seen, when we have a high load eccentricity, the position of the neutral axis can be found by solving this expression, Jn equal to X plus E prime by Sn, where Jn is the moment of inertia of the homogenized resistant cross-section, and Sn is the static moment of the homogenized resistant cross-section. We will write this expression by substituting the expressions for Jn and Sn. So we obtain this relationship. This is the expression for the static moment Sn, that multiplies x plus e prime minus the expression for the moment of inertia Jn, which is this one. Equal to 0. Well, this expression, after some simplification, becomes the equation we have already seen, that is here reported. That is well, by substituting the numbers, we obtain this expression, which after the calculations gives this third order equation, x cubed plus 600x squared plus 361,800 minus this last term here. Well, this equation has a unique real solution. So if we solve it, we obtain the position of the neutral axis, which is x equal to 270 millimeters. Well, in order to calculate the stresses on concrete and on the reinforcement, we need the static moment Sn with respect to the neutral axis. So we calculate it, since we now know which is the value for x. So we have that Sn is equal, as usual, to this expression, bx squared over 2 plus n as prime by x minus c minus n as by d minus x. While substituting the numbers, we obtain this expression. Which gives 9,850 by 10 to the power of 3 cubic millimeters. So we can now calculate the stresses. we have sigma C, that is equal, if you remember, to n over Sn by x. That is 300 by 10 to the power of 3 in order to obtain Newton over Sn by x, which gives 8.2 megapascal. Sigma S is equal to n sigma C over x by d minus x, according to the expression we have already showed. So we have 15 by 8.2, which is the stress in concrete already calculated, over 270, the position of the neutral axis, that multiplies 570 minus 270. That gives sigma S equal to 137.1 megapascal. Well, we can do the same thing, of course, for sigma S prime. That is n sigma C over x by x minus C. That gives 15 by 8.2 over 270 by 270 minus 30, the concrete cover. We obtain 109.3 megapascal. And this is a way for obtaining the position of the neutral axis and the stresses on concrete and on the reinforcements in case of high load eccentricity.